Hi there, good evening. Tonight we're going to do a quick little talk about the introduction to stoichiometry and the idea of what a mole ratio is and how a mole ratio will help us to really make the connection in stoichiometry with how this all works out. So to start us off tonight, I wanted to come up with this really simple example of a hamburger. And you might not like hamburgers, and that's okay, but just try to follow along with my analogy for just a couple of minutes and we'll figure out what's going on. So when we look at what's happening here for this hamburger, we can notice that one bun plus, I don't know, we'll say one handful of lettuce, we'll go with a handful of lettuce, plus 3 pickles, although those look a little bit more like cucumbers, but we'll go with pickles, plus 1 patty, as in hamburger patty, plus 3 tomatoes, and that's going to give us 1 burger. Okay, so if we were to look at this as being a chemical equation, we can go ahead and, where's my thing here? Oh, I know why it's all confused. Got it all figured out. If we were to look at this as being one chemical equation right here, oh, better undo that. Still learning my way here. If we were to look at this as being one chemical equation, we could see that one bun, slide this down here, which is going to go with all this other stuff right here, a handful of lettuce and 3 pickles and 1 patty and 3 tomatoes, are going to give us 1 burger. And that's all slid there really funny, so let's see if I can slide this all over a little bit more. Sorry about the confusion here, just trying to get it all on the same page. Okay, and that's going to give us the recipe for a burger. But the question we have to ask ourselves is, what's going to happen if we want to make, well, if we want to make 2 burgers? Well, it should make sense intuitively that if we want to make 2 burgers down here, then we would need to have 2 buns, 2 handfuls of lettuce, 6 pickles, 2 patties, and 6 tomatoes, because we're going to double that recipe, and that's pretty logical. But now let's do some weird stuff, okay? Let's say we're not going to create 2 burgers, but rather we want to create 1.39 burgers. Okay, if we're going to create 1.39 burgers, we have to ask ourselves, well, first of all, why would we want to do that? But second of all, how are we going to have to do everything else here? Well, we need to realize that we can recognize that there are some ratios that exist. Sorry about that, I'm getting ahead of the game here. Push my button. We can see that for every 1 burger that we're going to create, we're going to need 1 handful of lettuce. So it would make sense that if we had 1.39 burgers, we would need 1.39 handfuls of lettuce. But here's how this works. We can recognize that the mole ratio that exists is that for every 1 burger, we're going to need 1 handful, pardon the shorthand here, of lettuce. And if we look at this from the same perspective of our dimensional analysis we've done early in the year, the burgers are going to cancel. And we can see that that's going to equal 1.39 times 1 handful of lettuce, which is going to be 1.39 handfuls of lettuce. And I know that was really simple, but that's really how this process works. What if we wanted to figure out how many tomatoes we would need? Well, we would still take our 1.39 burgers, and we would say, all right, well, we're going to multiply that by, for every 1 burger, we're going to require 3 tomatoes, because we can see that for every 1 burger, they're going to be a requirement for 3 tomatoes. So now what we're going to do is we're not do that. We're going to say that this is going to equal, with our cancellations here, we can see that the burgers are going to cancel, and it's going to be 1.39 times 3. So when we go over to our calculator over here, it's 1.39 times 3, which is going to equal 4.17. So if we had the ability to get 0.17 tomatoes, we could say, all right, well, we're going to have 4.17 tomatoes. All right, what this comes down to is that these quantities right here that I'm putting a box around are what are called mole ratios, okay? And I made this silly analogy with creating hamburger because I wanted you to understand that a mole ratio is really just a ratio that exists between substances in a chemical reaction. If we model this here as a chemical reaction, we can see that there are ratios which exist. For every 3 pickles in this reaction, you're going to need 3 tomatoes. So if you need 9 pickles, you're going to need 9 tomatoes in order to maintain that recipe. For every 1 handful of lettuce, you're going to need 1 patty. So 4 handfuls of lettuce are 4 patties. It is really logical, okay? If we look at a chemical reaction as being nothing more than a recipe for chemistry that's going on, then we can really gain a pretty good appreciation about how to do this. So let's take a look at a real example. No idea what I just did there. So here's our real example right now, okay? Chlorine is used by textile manufacturers to bleach cloth. Excess chlorine is destroyed by its reaction with sodium thiosulfate as follows. Sodium thiosulfate plus 4Cl2 plus 5 H2Os give you 2 sodium hydrogen sulfate or sodium bisulfate plus 8 HCl, which is hydrochloric acid. So the first thing we're going to do, we're going to keep this really simple right now. We want to identify what are the mole ratios that exist between sodium thiosulfate and chlorine. So if we look at this reaction, we can see that the sodium thiosulfate there and the chlorine is right there. So what that means is that for every 1 mole of Na2S2O3, we're going to have 4 moles of Cl2. But that's not the only ratio, because the other ratio is to say, well, for every 4 moles of Cl2, we're going to have 1 mole of Na2S2O3, sodium thiosulfate. And we can get this information by just merely looking at the reaction. Okay, you can see you got your 1 mole of sodium thiosulfate there and your 4 moles of Cl2 there. But the point that I want to make here is that these 2 reactions right here, I was pointing at it like it was a board, sorry about that. These 2 reactions right here, this one right here and this one right here, they're reversible. A mole ratio is nothing more than a conversion factor. Keep that term in mind, conversion factor, a multiplying number that allows you to convert between substances. We're going to come back to that on the next slide here in just a couple of minutes, so I want you to hold that thought. Let's take a look at letter B. Okay. Letter B, identify the mole ratios between chlorine and sodium hydrogen sulfate, the product. Well, we can see that for every 4 moles of Cl2, there are going to be 2 moles of sodium, Na, hydrogen sulfate, HSO4, NaHSO4. But also, for every 2 moles of NaHSO4, there are going to be 4 moles of Cl2. Again, this is an interchangeable ratio. Now, there's another thing I want to point out right here. You can see that this is a 4-to-2 ratio and a 2-to-4 ratio. Do not simplify that ratio. Okay? Do not simplify that ratio. The reason why we don't want to simplify that ratio is because that ratio comes directly from the balanced equations. Okay? So do not simplify those ratios, because if you do, and you go back to the balanced equation, you might find some confusion. We'll talk about how we can simplify the numbers later on when we work our way through the stoichiometry unit. Okay? So now let's look at letter C. Okay? Identify the mole ratios between water and sodium thiosulfate. So we look at the reaction, we can see for every 5 moles of water, there are 1 mole of sodium thiosulfate. So for every 5 moles of water, there are going to be 1 mole of sodium thiosulfate, Na2S2O3, but also we can flip that and say for every 1 mole of sodium thiosulfate, Na2S2O3, you're going to have your 5 moles of water. Okay, pretty straightforward, just coming right from the balanced equation. And then finally, the mole ratio between sodium hydrogen sulfate and hydrochloric acid. Okay, for every 2 moles of sodium hydrogen sulfate, NaHSO4, you're going to have 8 moles of HCl. Okay, but also for every 8 moles of HCl, you're going to get 2 moles of NaHSO4. Okay, again, flipping the reaction is something that is possible for us to do. And also with this 8-to-2 ratio, we don't want to simplify that one either. Okay, now let's put this to use. back to the same question. Chlorine is used by textile manufacturers to bleach cloth. Excess chlorine is destroyed by its reaction with sodium thiosulfate as follows. We got that whole reaction before. Now the question becomes, how many moles of sodium thiosulfate are needed to react with 0.12 moles of Cl2? So this is just like going back to our hamburger analogy and changing things up a little, okay? Instead of making only one burger, here, we wanted to make 1.39 burgers. Come back over here to this example over here, and we can see that instead of making only instead of requiring 4 moles of Cl2 here, I'm pointing at the board again, 4 moles of Cl2, we only need 0.12 moles of CO2. So how are we going to set this up? Well, let's keep it really simple, okay? We're going to start with the 0.12 moles of CO2 that we read in the reaction. We know that we have 0.12 moles of Cl2, and we're going to put that over 1, because what we are trying to do is to convert from moles of Cl2 to recognize the moles of sodium thiosulfate. That goes back to that term conversion factor that I spoke of before. When you go from moles of one substance to moles of another substance, you are using the mole ratio as the conversion factor. So what is the mole ratio? Well, the mole ratio is for every 4 moles of Cl2, you're going to have 1 mole of sodium thiosulfate. For every 4 moles of Cl2, you're going to have 1 mole of sodium thiosulfate. Well, we want to cancel our moles of Cl2. So we're going to put our 4 moles of Cl2 in our denominator for every 1 mole of sodium thiosulfate, Na2S2O3, in our numerator. Now we can see that our moles of Cl2 are going to cancel, and what we're left with is 0.12 times 1 mole of sodium thiosulfate divided by 4. So if we write that down, 0.12 moles of sodium thiosulfate, Na2S2O3, divided by 4. We can now simplify that to say 0.12 divided by 4. Don't really need a calculator, but just because I have it here, 0.12 divided by 4 is equal to 0.03. 0.03 what? Come back over here, 0.03. We want to maintain 2 significant figures, 0.030 moles Na2S2O3. The ratio is now the same. That same 4-to-1 ratio that existed before, 4-to-1, is now in place here, 4-to-1. Okay? All right, so I want to keep that in mind. All right, next example. How many moles of HCl can be produced if 0.12 moles of water react? Well, we're going to do the same thing. 0.12 moles of water, we're going to put that over 1. This time we're trying to convert from moles of water to moles of HCl. So we can see that for every 5 moles of water, there are 4 moles, we don't care about Cl2. For every 5 moles of water, there are 8 moles of HCl. So now we're going to multiply that by that 5 moles of water to 8 moles of HCl ratio. So where's the 5 moles of water going to go? Well, the 5 moles of water has to go in your denominator. How do we know it's got to go in your denominator? Because the moles of water are in the numerator up here, and we want them to cancel for the purposes of converting, conversion factor. 5 moles of water for every 8 moles of HCl. 8 moles HCl. We can see now that the moles of water are going to cancel, and what we're left with is 0.12 times 8. Now we'll go to the black ink here. 0.12 times 8, which is going to equal 0.96 moles of HCl. Hope I didn't make a fool of myself, and that's the right math. 0.96 moles of HCl divided by 5. And now we can go to our calculator and simplify that, which is going to be 0.96 divided by 5, 0.192 moles of HCl. We want to maintain our 2 significant figures, so we'll call that 0.19 moles of HCl. Okay, and this is going on faith that 0.12 times 8 is 0.96, which it is. Okay, last example. All right, and we'll go to blue ink this time. How many moles of sodium hydrogen sulfate will be produced if 3.27 moles of hydrochloric acid are produced? Well, what's interesting about this one is that we have 3.27 moles of hydrochloric acid being produced right here, and we're trying to relate it to moles of sodium hydrogen sulfate being produced right here. Does it matter? No, because we know that there's an 8:2 mole ratio that exists between those two substances. You can relate any two substances to each other from a chemical reaction. And for that matter, you can relate any two substances to each other from two related chemical reactions that don't have the same substances within them. That's down the road. But let's work our way through this one. We have 3.27 moles of HCl. We're going to put that over 1. And we're going to multiply that by the mole ratio that exists. For every 8 moles of HCl in the denominator, so that it cancels, 8 moles of HCl in the denominator, you're going to have 2 moles of sodium hydrogen sulfate in the numerator. 2 moles NaHSO4. Okay? And again, I would point out we do that so that it cancels. Moles of HCl cancel. 8 moles of HCl, 8 moles of HCl. When we work our way through that, we can do this and figure it out. It's going to be 6.54. 6.54. The unit's going to be moles of NaHSO4 divided by 8. And 6.54 because 3.27 times 2 is 6.54. And then we can come over to our calculator and we can say 6.54 divided by 8 is going to equal 0.8175. We'll maintain 3 significant figures, which is going to equal 0.818 moles of NaHSO4. So essentially what we've done here is we've maintained our cheeseburger recipe. Okay, we've scaled it up in each case, we've scaled it down in a couple of cases, but that's how this works out. Okay, one more simple example and then we'll be all set here tonight. Okay, how many moles of oxygen are needed to fully react with 6 moles of octane? Well, let's just jump right in. We're going to start with 6 moles of octane. I read the question before going back to the beginning. I apologize for that. The octane in gasoline burns according to the following equation, and we've got that equation right there. Okay. Now we can ask, if we've got 6 moles of octane, 6 moles of C8H18, we can put that over 1. And we're trying to get to moles of oxygen. So we can see that there's, for every 2 moles of octane, there's 25 moles of oxygen. So 2 moles of octane, C8H18, for every 25 moles of oxygen, O2. Come over here, our moles of octane cancel. Well, 6 times 25, which is equal to 150 moles of O2 divided by 2. We don't even need to go to our calculator for that. We can see that it's going to be 75 moles of O2, maintaining only one significant figure. We would call that actually 80 moles of O2. Okay, pretty simple, right? Next example. How many moles of carbon dioxide can form from 0.5 moles of octane? Well, octane to carbon dioxide, okay, 0.50 moles of octane, C8H18, put it over 1. And now we know that it's going to be a 2 moles of octane to 16 moles of CO2 example. In the denominator comes 2 moles of C8H18 for every 16 moles of CO2. Okay, nice easy numbers here again, 0.5. Back to this here actually. We got our moles of octane that cancel. 0.5 times 16 is 8 moles of CO2 divided by 2, which is going to simplify to 4 moles of CO2. Nice and easy. Okay, again, setting it up, here's our mole ratio. Now it's just a matter of multiplying it by the conversion factor. Next example, how many moles of water are produced from the combustion of 8 moles of octane? So we'll start with 8 moles of C8H18, and we want to know the moles of water over 1. We can see when we look at the reaction, for every 2 moles of octane, there are 18 moles of water. So for every 2 moles of C8H18, there are going to be 18 moles of H2O. We can see again, this is going to cancel. Your moles of octane are going to cancel. You're going to be left with 8 times 18 divided by 2, which I can't do this in my head, but this is where I can show you a little shortcut we were talking about before. I told you I'd be able to show you an area where you can maybe simplify this a little bit. You can see 18 over 2 can be simplified, right? So we can go ahead and break this down to say, okay, 18 over 2 is the same as saying 9 over 1, okay? So now we can actually simplify this, and we can say, all right, 8 times 9 is equal to 72 moles of H2O over 1, or 72 moles of H2O, okay? And then the last example right here, scroll down just a little bit. The reaction is used to synthesize 6 moles of carbon dioxide. How many moles of oxygen are needed? How many moles of octane? Okay, so we're going to take and we're going to say, all right, let's go to purple this time. 2 different questions. 6 moles of carbon dioxide, how many moles of oxygen? And then 6 moles of carbon dioxide, how many moles of octane? 6.00 moles of CO2 over 1 times, we can now see for every 16 moles of CO2, we are trying to get the oxygen, 25 moles of O2. So we come over here, 16 moles of CO2 for every 25 moles of O2. Not sure what that blue line is. Hopefully it's not bothering you too much. Can't do that one in my head. What I can do is I can recognize that the moles of CO2 are going to cancel. And we're going to go over to our calculator here. And we're going to say, okay, 6 times 25 is equal to 150, as we did before, divided by 16, which is going to give us 9.375. So we come back over here, 9.38, 3 significant figures, 9.38 moles of O2. Okay, and to that point, just to kind of keep everything going on the same page here, we're going to start with the same 6.00 moles of CO2, put it over 1, and we're going to notice that for every 16 moles of CO2, we want to know how many moles of octane, 2 moles of octane. For every 16 moles of CO2, we're going to have 2 moles of octane, CaH18. Come over here, moles of CO2 cancel. Here's a little shortcut rule. Okay, 2 over 16 is the same as 1 over 8. So now it becomes 6 times 1 is 6 divided by 8, which is equal to 0.75, 3 significant figures, 0 moles of CaH18. Okay, don't believe me, you can go to your calculator and figure it out. All right, one last thing I want to say and then we'll be all set. All right, the most important thing that you need, in order to figure out mole ratios is a balanced chemical equation. Okay? So what that means is that you need to remember how to balance equations, or you need to go back to it. Because what it came down to is in this example, it was already balanced for you. Okay? In this example, it was already balanced for you. If we go back to our hamburger, this equation was already given to you. All right, you need to make sure that you are able to balance chemical equations in order to work your way through this. So one of the first exercises you're going to need to do is you're going to need to be able to balance chemical equations. Keep it really simple, okay? Use your atom inventory and you'll be all set to go. Once you've identified mole ratios, you're ready to roll forward with stoichiometry. The mole ratio is the most important aspect of what you are going to do for much of the rest of the time that you are in chemistry. If you can figure out mole ratios, you are good to go. Okay? Hope this video was helpful to you. Hope you're able to work your way through some of your mole ratio types of calculations. And I look forward to giving you the next video in the series.